Okay, so we'll get the exams back, I'm hoping, on Wednesday. Yeah, someone's excited. So we don't want to have any, how do you pronounce it, do or do? Do. There, that's it. Say it again. That's good. Dope. I don't have any dope moments, so that's why we want to make sure we use a full systematic treatment of equilibrium in certain situations, right? And we're going to get into some convention like formality and fraction of dissociation, and see why they're important a little bit. Probably it's kind of hard to explain right now without defining what those words are. But in the interest of talking about formality and what's coming up, let's review what the 6 strong acids were. Nyla, what was one of them? HBr. Yeah, Jeff, keep going. HNO3 are nitric. Hydrobromic, nitric, Kimberly. H, hydrochloric acid. Erica, we're halfway there. HI, hydroiodic acid. Oh, Pablo. Perchloric acid. One more we're missing, Kat. Sulfuric, H2SO4. Okay, the 6 strong bases. Amanda. NaOH, I think she said, right? NaOH. Pedro. KOH. And Kathleen. Where is she? Where is she? LiOH. Okay, so we're following the solubility rules. Good so far. Adrian, now the exceptions to the solubility rules. Listen to Natalie, I think she said it. CaOH. Now, but this isn't the formula though. 2, because calcium has a +2 charge. Calcium. What's the other one? Calcium hydro. The exceptions to the hydroxide solubility rule. Calcium, strontium, and barium. And they're all powers of 2. Okay, and we'll get to why we're reviewing that in a little bit. But pH is the negative log of the hydrogen ion concentration. John, you should be happy that it's almost like the sig fig story in Gen Chem. We did it once, and we never did it again. I say pH is the negative log of hydrogen ion concentration. What is it supposed to be? Negative log of the activity of the hydrogen ion. Okay, but see, we're already just throwing it to the wind. That's just how the book is. That's how the system is. So I'm just going to follow what the system is, what we're doing. pH and pOH are 14. And at Miranda, what pH values is it acidic? Low. Yeah, low pH values. Okay. In pure water, and I should say 2 Miriam at 25 degrees Celsius in 1 atmosphere, what's the concentration of hydrogen ion? What is it? Does anybody know? Anyone help her? 1 times 10 to the negative 7. Now, how do you know it's 1 times 10 to the negative 7? Yeah, it's half that kW. If you don't see it, he probably is kind of important. That kW is 1 times 10 to the negative 14. This is how the folks are getting the answer. That has to be hydrogen ion times hydroxide. Right? Okay. So hydrogen ion and hydroxides produced from water dissociation. Anna, is the hydrogen ion concentration produced from water dissociation, right? First off, is this produced from water dissociation? Let's ask Anna that. Where is she? Is this produced from water dissociation? Autoprotolysis, water decomposition? No? Yeah. Right. Where else would it come from? It has to come from water falling apart because it's pure water, right? Does that make sense? The concentration of hydroxide, 1 times 10 to the negative 7, has to come from water falling apart. 1/110th of a billionth, right? Okay. No, yeah, a millionth. Sorry, millionth. So it's a small number, but it is happening. So the question is the concentration from the hydrogen ion, Danielle, always 1 times 10 to the negative 7 molar? Not 25 degrees Celsius in one atmosphere? No, it's not. Why? You could have other stuff to influence. You could have a common ion effect problem. Let me show you an example. If I had 0.1 molar HCl, just pretend. You have 0.1 molar HCl. Casey, you could say the total hydrogen ion concentration is what? 0.1, because it's a strong acid. Okay, so you can say the concentration of hydrogen ion, maybe put a little total or something, I don't know. That's going to be 0.1. We could say, well, what fraction of this is from water falling apart? That's what we're getting in today. It's going to be minuscule because this is a huge number. But if we could still figure it out, I think it's useful. Okay, if I calculate the fraction from, what do we call that? Water dissociation. H2O dissociation. That would be the fraction that's actually coming from water dissociation divided by our total, 0.1. How would we get that one? Nyla, how would we get that top one? Because if we did, the answer would be yes, but we said it was no. We should write no there. And we're going to prove it. That's what we're trying to do. We're trying to prove it. And let's prove it. Prove it. Okay, that's what we're doing here. I'll give you a hint. See if anyone can see this. There's an equilibrium going on with this water dissociation. It's what? H2O going back and forth to H plus and OH minus. Do we have space for that here?
So would you use the KW, the ice table?
We're getting there. Okay. So this KW always holds. KW always holds. KW has to be 1 times 10 to the negative 14. This has to hold, always. All right. But we're still not there yet. How do we get a number right here? It's not too... We're going to need it. Okay. There's a concentration. So first...
Would it be that and
you just don't... You might be right, but let's just make sure you see it. Okay. Does everyone agree with me so far that you can't stop water from falling apart? You can't stop it. Okay. So there is a number. There is a number that goes right there. But it's not 1 times 10 to the negative 7. Because we've got this bloody common ion effect thing going on. It's going to be a lot smaller or bigger. Well, we can calculate it. We can put in, I guess what I'm asking is this. Have we added any hydroxide? No, all we have is 0.1 molar HCl. So if there's any hydroxide, it had to come from what? Water falling apart. So all we do is we calculate the concentration of hydroxide, because that has to be from water falling apart. And remember, that's 1 to 1. Where's our reaction here? Well, it's 1 to 1. So if you produce 1 hydroxide, you're going to produce 1 hydrogen ion. So we're going to find the concentration of hydroxide and just say, well, then that same amount had to, go to hydrogen ion. So let's see what hydroxide is. Hydrogen ion is what number? 1 times 10 to the negative 1 times 10 to the negative 1, right? So this guy is 0.1. So we can calculate him. Concentration of hydroxide must be, let's see, multiply that times. That's 1 times 10 to the negative 15. I can never do anything in my head. 1 times 10 to the negative 13. I'm so bad. Okay. 1 times 10 to the negative 13 molar. That's the concentration of hydroxide. Everybody agree? Because this Kw always has, it's an equilibrium. Can't stop it from happening. Concentration of hydroxide is 1 times 10 to the negative 13. We didn't add any OH, so it means that complete population is from water falling apart. Well, if that's from water falling apart, the concentration of a hydrogen ion from water falling apart would be what number? It's 1 to 1. 1 times 10 to the negative 13. Right? Because water falls apart 1 to 1, H plus and an OH minus. For every OH minus, you get an H plus. So if the hydroxide concentration from water dissociation is 1 times 10 to the negative 13, well, then so must H plus be from water dissociation, not the total. So you'd put 1 times 10 to the negative 13 up there. Divide it by 0.1. You get some really dinky numbers, hardly anything. 1 times 10 to the negative 12. Multiply it times 100 to get percent. That's 1 times 10 to the negative 10. So no wonder that's 1 times 10 to the negative 10 is the fraction due to water falling apart. We do not need to do a full systematic treatment of equilibrium, because this is minuscule. 1 times 10 to the negative 10, all right? A tenth of a billionth. So we don't worry about it. We don't need to do full systematic treatment. Okay? However, you can see it coming. If you work a bunch of these, you find a range where, we have to use full systematic treatment. It's in the book. If I remember, I want to make sure I think it's 10 to the negative 6 to 10 to the negative, you remember this? It wasn't so clear in the reading. 10 to the negative 6 to 10 to the negative 8. It's got to be in here somewhere. Well, it's 10 to the negative 6 to 10 to the negative 8. When you're in that range, you take a strong acid, one of our 6, and they say the concentration is 10 to the negative 6 to 10 to the negative 8. Then you got to worry about a full systematic treatment of equilibrium due to the dissociation of water. Right. Yes. Yep, because that's the amount from the water falling apart, and then you divide it by the total. So take that, divide it by 0.1, and that'd be your fraction. If you like percent, multiply it times 100. Okay. Well, you can do it whenever you'd like. Just all right. If it was if it's not one, it'll be a little more complicated, but it's the same story. Doesn't matter what the ratio is, it's the same story. Okay. Oh, we just did it. We got all this nice space in here. Okay. Well, see above. Okay. Does that make sense? So a water, you can't stop water from falling apart, but you can get its fraction of dissociation.
There would be a percentage?
If you want, you can call it like
I mean, like, would
percent,
that be a-
fraction, percent, right? Otherwise, just fraction is just one over the other. You could say percent, though. Okay, and we'll get into percent and coming up in a little bit. We're going to have a little equation with percent in it. But this idea of formality. I don't know if you've done any labs that they had, instead of 0.23 big M HClO4, they have F. Or wherever. The concentration unit isn't molarity, it's formality. Formality is what over what? It's still moles over liters. The difference is it's moles of what over liters. It's kind of like the mathematicians getting involved here. If you write 0.23, I don't know, big M of anything, I don't care, NaCl, you're saying that exact concentration is 0.23 molar. That this NaCl, right, NaCl, that this thing exists and its concentration is 0.23 molar. That's what it means when you write big M. Well, NaCl doesn't even exist in solution. See what I'm saying? Na plus does and Cl minus does, but NaCl doesn't. So technically, you shouldn't write big M. You should write big F. That's the one. All right? It's kind of good and it's kind of confusing. In something like this top one, I think it's kind of confusing. But why does big F make sense for 0.23 formol per chloric acid? Because it's a strong acid. Does HClO4 even exist? No. So F is the idea of, well, let's jump down to this one. 0.23, especially here it makes sense because we're used to this full systematic treatment. If you write this, that means the concentration of HCN is 0.23 molar. That's what it means. If you write an M. If you write an F, no. The concentration of cyanide in all its forms is 0.23 molar. Big difference, right? And we know that from this full systematic treatment. So formality is, we should probably write that in English, right? The concentration of cyanide in all, or you can say the concentration of, here, just why even make it, let's say the concentration of HCN. Do it this way, because it's FHCN. So it could be F whatever, who cares, FX. The concentration of this X thing, whatever it is, in all its forms is 0.23. Right? So it doesn't really matter what this thing is. Whatever that big blob is, you put it right here and say the concentration of that thing in all its forms is 0.23 molar. So they're taking into account all the different forms. And we've seen that problem, especially with a weak acid. That's a big deal because you have HCN that exists. You have its conjugate base, CN minus. And we've seen that already. If you don't take that into account, you get way off on your pH predictions. Okay. So I guess the story is we were BSing you again for this full systematic treatment. You saw these big M's. You shouldn't have seen a single big M. You shouldn't have seen a single big M on that whole sheet. Should have been F's everywhere because things exist in more than one form. We should have been talking about formality to be technically correct. Okay. Any questions on that? Okay, it's just kind of like a technicality. But we need to survive, live with it. Weak acids and bases. Let's do a little review here. How do we write a Ka reaction? Right? If Kimberly, if our weak acid is HA, how did you write the Ka reaction? HA goes to H plus and A minus. And we're used to doing this, okay? Except just kind of go back. You have 0.23 FHCN. It's the same thing we did before. If you want to get the pH, you do ice, right? However, now you're going to use the formality as initial concentration, which is technically a better way to, it's just technically correct. So nothing really changes, right? Dashes. You remember this? Then you have minus X and X's. You remember? So it's no big deal. I mean, it's just technically it's so much. It takes into account that cyanide or your weak acid. It has two forms, so you should be using an F in the first place. Okay. So nothing's really changed. How about a Kb reaction? Erica, how did we write a Kb reaction if our weak acid is HA? Yeah, we're going to add water. Water plus, not HA, A minus, because we have our conjugate, we have our base there. Conjugate base yields HA and OH minus. So the same thing. They're going to give us some formality of cyanide, sodium cyanide or something, sodium fluoride, some conjugate base of a weak acid. And you do ice, right? And you stick that initial formality right there. Right? And we do the same thing we did before. Right? If you want to fill it all out to make it look nice. Whoop, this guy is going to be that formality, that number minus X. Okay. Now here's what the book wants to talk about. What's the fraction of dissociation of some weak acid? All we do is we get the X in ice, divide it by that original formality, and we'll have our fraction of dissociation. Okay. So to get the fraction of dissociation of weak acids, the X in ice, divide it by that initial formality, right, concentration, and we'll have it. So it's something that you should probably know to get through the homework. Find the pH of 1 times 10 to the negative 3 molar HBr. Pablo, is this a question you like to see or not? Yeah, why? Strong acid, number 1, so you don't have to write a Ka. And number 2, what? So now see how there's two qualifiers now? He likes the strong acid, but he also has to like something else. We should have an F in there, true, but what? It's that. You're supposed to like this. Where is it? That thing I forgot. Right? Two things you got to watch out for to make it a happy question. You want it to be in this. You don't want it in this range. If you do, what happens? Full systematic treatment. I don't care if it's a strong acid. Full systematic treatment of equilibrium. Right? Okay. Yeah. pH is going to be the negative log hydrogen ion. No, it's just like sig figs in general chemistry. We did it for one exam and then we said goodbye. Even though look, they're really, really important.
So no more activities at all?
Not until a final exam. But it's in a sense it's kind of more efficient, but you don't have to be interpolating all the time. But if you did, you get really good at it. But okay, what's that? 1 times 10 to the negative 3 is 0.001, and you take the negative log of that, and you get what, 3? Okay. Find the pH of 5 times 10 to the negative 8 molar HClO4. Yeah, good. I'm glad I hear it. Uh-oh. The problem is the range. Okay. So that means what, Kat? Dr. Smith's 5-step program. Yeah, Amanda, what are you going to do first in the 5-step program? All the what? All the ions. So give me a couple of them. Good. Notice she did not say HClO4, right? So you do not say HClO4. Again, there it is, see? And I copied this from the homework. That shouldn't be big M, that should be... See how they're already forgetting it? They're in the same section, and they're not even doing it. Whatever. Okay. So... No, see how really unimportant it is. It's just a technicality, but it looks better if you have it. So now we are at Kathleen. Now what would you do? Okay, can we write any KAs? Nope. So we have to write. Well, we can write something, Adrian. What can we write? Anybody help him? We can write KW 1 times 10 to the negative 14. Hydrogen. Are there any other K expressions, John, we can write? No. Okay. Oh, Miranda, what should we do? Before. We have to add the OH minus to our list. Right? Because we just wrote a K expression and we introduced a whole new ion. We better add him to our list. Right? Okay, Miriam. Now what would you do? Charge balance, yeah. I like doing that before mass balance. Sometimes you can get away with it. Okay, so all the cations on one side. Is it plus or minus? I mean, is it plus, minus, or times, or divide, or what? These always plus. Anything with a charge. Okay. How many equations? How many unknowns? Do we have more to go, or can we start plugging and chugging here? What'd she say?
Oh, one more.
Okay, and what would it be?
Oh, the chloroenol form, isn't it? Equals 5.0.
The ClO4, that perchlorate, equals 5.0 times 10 to the negative 8. There's no other source for perchlorate. And it's a conjugate of a strong acid, so you can't write a Kb. So it's just going to be sitting there. He's just sitting there. So the concentration of perchlorate in all its forms has to be 5 times 10 to the negative 8. And you're looking up here, there's no other chlorates in any other form, so you quit. Now we've got 3 equations, 3 unknowns. Good deal. Okay, Danielle. Now what? Mm-mm. 3 equations, 3 unknowns. So we just have to keep substituting and rearranging until we finally get 1 equation with only 1 unknown in it. I might do that one first just to get rid of 1 unknown right away. Right? Put this guy in up here. There's a lot of different ways to do this. Danielle was starting to rearrange this guy. You can. I just like to get rid of that darn chloride. He's just bothering me sitting there. Right? The concentration of hydrogen is 5 times 10 to the negative 8 plus hydroxide. Okay. Now we've got two equations. Two unknowns. Casey, what would you like to do? Okay, she wants to solve the Kw for the concentration of OH, then plug it into 2. Good deal. Okay. So let's rearrange 1 and substitute into 2. All right, so rearrange 1, we'll get 1 times 10 to the negative 14 all over the hydrogen ion is hydroxide. And then if we substitute, into 2, we're going to have concentration of hydrogen ion equals 5 times 10 negative 8. And my hydroxide now is going to be that guy. Plus my hydroxide, which is 1 times 10 negative 14, all over hydrogen ion. Okay. You can call that 3 or something. So let's fix that equation number 3 up. Nyla, what should we do? Yeah, here we are, right here. Yeah. Here she said, multiply all the terms by the hydrogen ion concentration. Good. And then get it in the form of the quadratic. ax squared plus bx plus c equals 0. So I'll have hydrogen ion squared. I like to have my little a be a 1 and positive. It's just how I like to do it. So I'm going to leave him where he is and just bring the other stuff over. It really doesn't matter. Okay. Does anybody know what this means? You write something here, and then this little guy, and then something else. What does this mean? Kind of like the next step. Implies. Implies. What's therefore? 3 dots. That's therefore. If you like to play around with that stuff. Okay. It's in the right form. Okay, so that means my little a is 1. I need negative b plus or minus the square root of b squared minus 4ac all over 2a. All right? So I'll have 5 times 10 to the negative 8 plus or minus the square root. Man, I have no space here. Five times 10 to the negative 8 plus or minus square root 5 times 10 negative 8 squared. All right. Well, it's supposed to be negative, but you square it, so minus 4a c is a negative 1 times 10 to negative 14. Okay. Let's write a couple steps here. See if you agree with me. 5 times 10 to the negative 8 plus or minus 2.06. Okay, did you get this for your square root part? Okay, good. It doesn't make any sense to do the minus one, so I'm just going to do the plus one. So 2.06 times 10 to the negative 7 plus 5 times 10 to the negative 8, 2.56. Oh, I got to divide by 2. So about 1.28. So my x is about 1.28 times 10 to the negative 7. And what is my x? My x is hydrogen ion concentration. Okay. Okay. What is the question anyway? Calculate the pH. So we just take the negative log. About 6.89. All right. So Miranda, how are you going to do this? No. It's HClO4. It's the same thing we talked about a little bit earlier. Let's set it up. This might help. The fraction. The fraction from dissociation of water. Okay. It's the amount from water falling apart divided by the total. So which one do we know the total of? The hydroxide or the hydrogen ion? We just did hydrogen ion, right? Okay. And thereafter, that's really what they're after, right? They're talking about hydrogen ion. What fraction of the total hydrogen ion? So we have to be sticking with hydrogen ion. So what's the total? We just found it to be 1.28 times 10 to the negative 7. Okay. How do we get the top part? It's going to be the OH. Oh, you already did it? Oh, you did? Okay. So if you did it my way, you'd probably have to go back up to any equation works. I would probably just use this one. Plug in our concentration of hydrogen ion. We get OH. Did we add any OH at all in this system? It was just 5 times 10 to the negative 8 perchloric acid. We didn't add any OH. So if there is any OH, and there is, it's all from water dissociation. So you said you got the hydroxide concentration to be, what was that? 7.8 times 10 to the negative 8. Okay. So we put that up on top. And what do you get? Point what? 0.609. Well, 0.61. That make sense? Okay. Let me just reword it a little bit to help the magnitude of this issue come into play. What percent of the hydrogen ion in this system is from water dissociating? 61%. Over half. So that's why that range is a big deal. It's significant in that range. Okay. So go ahead, work together on the rest of these. We have about 10 minutes. See if you can knock these out. Is from water dissociation. Yeah. They didn't ask about percent, but it seems like percent's easier to conceptualize. For you organic folks, if you want to do this the technically correct way, which H is the acidic H? The last one. Yeah. So when you write your Ka reaction, you should be ripping off that last H. So that one's not so bad. In number 6, remember the fraction of dissociation is just X all over that original formality. And the X is the Xn ice for the Ka reaction. Right. Not sure, just ask.
So this is concentration of
That's the initial, yep. That should be a bloody F again, right? Should be a bloody F. Homework isn't even following its own rules. But notice how it really doesn't matter. But what were the rules? Remember what we said it was? I think it was -3. You're in trouble. -5 seemed to be okay. -5 seemed to be okay. I mean, you can go ahead and drop it, get your answer, then go back and see if it's close to 0.1 or not.
I'm just saying because I don't know the rules for this.
It's the same.
Okay.
It's the same. It's the same.
So we drop it.
The only place where we were BSing you, Nyla, is that big M. We should have been saying F. Other than that, everything else is the same. So yeah, we should point out one thing though. I mean, this. You notice how you're interested in this, in judging whether you can drop the X or not. Notice this is also something you need to worry about. If this was 0.0001 or something, then your X is going to be a lot closer to it than it would be. See? So you have to worry about this number and that one. Usually this one decides everything, but this one you got to be careful with. If it's dilute, if it's really small, you're going to have a hard time dropping that X. So it'll be appreciable. Yeah.
This is for the
That's
H, or is it
no.
the
It's the 0.1 molar F or M of a solution of weak acid HA. So
Okay,
it
so
corresponds with the HA. Remember, HA you have to have an equilibrium constant, so you don't have dashes there. Mm-hmm. Yeah. 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 Something there. Man, we're missing 9.8. We're missing the Ka. 1.58 times 10 negative 10. That should be in there. Otherwise, you have to look it up. All right. Oh, so in this one, it's a little difficult to recognize. You know it's going to be like this. Right? You know what? But what's what? This one is the HA. There you go. This one's the HA. This one's the A minus. What is this thing then?
Just the initial.
Yeah, the initial, but which form is it? Why is it the acid? Why is this the acid form? Well, if you like leaving groups, I don't know, that's not the right term, but the chloride, Cl minus, right? If you put in the little charges here, you recognize here's your weak acid, and this guy's Cl minus. So it's just a weak acid with a Cl minus on it, making it a salt. I mean, it's the same as HCN or something like that, but not HCN, kind of like, we don't have anything like this, right? Kind of thinking that the conjugate acid has a positive charge. Usually we just have our conjugate base alone. But this is our, right? Well, maybe it'd look better if we did this. Put a little plus here and a little minus there. That probably would look better. Then you can see he's the initial conjugate acid, right?
So the CO is the A minus?
No. Here's your conjugate base. Here's your conjugate acid. No, because recognize, see how the conjugate acid has a plus on it. So if you write the Ka reaction, you lose an H plus, it's going to leave a neutral conjugate base. That's why he doesn't have a charge on him. That's why it looks unusual. We're just not used to seeing a weak acid that form. Okay. This one is the, which one? Conjugate base. How can you tell that this is the conjugate acid and that's the conjugate base? It has one more H. Yeah, it has one more H. So you'd write here the conjugate acid over here. Goes to H plus and right, rip off an H plus off of this thing, right? And you're going to be just left with that. There'll be no charge on it, just like they said up here.
But it doesn't matter as long as the charges are bound to either side. That's why you have a plus and a plus, correct? Okay.
Right? The H plus and the conjugate base. Do you recognize, though, you don't even have to write this? It's hard to feel comfortable not writing it. I understand that. But you don't have to write this. All you got to do is just write the HA one and recognize where the initial concentration goes. That's the only place you can screw up. Miriam. What's that? What's that? No, we lost it. Oh, sorry. We lost it. I wrote it. We lost it. We lost it. Sorry, we lost it. All right. That should be the acid form. Yep. Because if it was the conjugate base form, we have to write a Kb reaction.